In this video, we're going to see a very different type of generative model, and this is based on something called a diffusion process. So the overall kind of mental model you should have in mind here is that a diffusion process starts with some real data, so let's say, for example, an image, and in the forward diffusion process, we gradually corrupt the image by adding more and more noise to the image until eventually we've reached just pure noise. Then the generative model aims to try to reverse this process. So in other words, starting from noise, try to gradually denoise the image until we end up with a realistic and completely noise-free image. So we're going to look in this video in some detail at a specific version of this idea called the denoising diffusion probabilistic model. So we're going to clarify some of the maths here a little bit more precisely. So we're interested in what's happening between each of these steps. So as between each time step, we're either adding noise if we're moving in this direction, or we're denoising if we're moving in this direction. So Q of x0 is the real data distribution. So imagine the space of all real images, for example. So this image over on the right is one sample drawn from this real data distribution. But of course, this itself is really difficult to model. That's what we're trying to do with this generative model. But what we can do is sample from this real data distribution by just choosing a training image. So x0 is just a sample taken from the real data distribution by just taking one of our training images. Then this conditional Q is the forward diffusion process. So what this is saying is, given an x at time t minus 1, what is the distribution of possible xt's at that point? So those are all the xt's that I could get by adding a certain amount of noise to my xt minus 1. And that's modeling the forward diffusion process. So basically start from a real sample, gradually add noise until we've ended up with some x capital T that is very close to noise just drawn from a standard normal distribution. So in other words, all traces of the original x0 have gone. So we end up with a sequence x0 through xt to x capital T, where xt is pure Gaussian noise. And then the tricky bit, the interesting bit, is to try to learn the backward diffusion process. So we're going to call the backward diffusion process P. Because it's learned, it's going to be a neural network that has some weights, theta, so those are the things that we're going to try to learn. And it's simply trying to do the opposite process. So now it's given an xt, so conditional on that xt, what is the distribution of possible slightly less noisy xt minus 1s? So we'll just dive a bit deeper into the forward and backward processes. So just to clarify, so this backward diffusion process is saying, given a noisy sample, try to predict a slightly less noisy sample, or the distribution of those slightly less noisy samples. So let's just talk about the forward diffusion process. So we start at time t with some real sample, and we add noise until we get to time capital T. And we have to define a variance schedule. So this is a variance associated with each of the times, and they should be monotonically increasing in between 0 and 1. And different methods differ by how they define that schedule, but we're not particularly interested now how that's defined. So the forward process essentially defines a normal distribution. So given the slightly less noisy sample xt minus 1, my distribution for what xt is going to look like after we've added a bit more noise is a normal distribution where the mean is my previous sample, scaled by this factor that depends on my beta, and the variance is just the beta. So that's my variance schedule changing at each time step. So what I can do is, as we did in a variational autoencoder, rather than drawing directly from this distribution, I can instead just sample some noise epsilon from a standard normal distribution and then just scale appropriately. Now, one neat and important trick is that actually I can directly jump to an xt. So some point partway through this forward diffusion process, I don't have to start with x0 and then gradually add each of the bits of noise each time. I can go from an x0 directly to an xt that is equivalent to what I would have got by doing this one step at a time. So all I do is I define another normal distribution where, again, the mean is just x0 scaled by something that depends on my betas. And my variance also depends on my betas. So this alpha hat is like the product of all of these 1 minus betas. So you can see this variance is kind of accumulating over the steps up to time t. Okay, that's the forward process. Now in the backward process, we also kind of use a little trick. So instead of trying to directly predict the less noisy version, what I do instead is I predict the noise. So in fact, my network is not going to be on P, it's going to be on epsilon. Again, this is a neural network, so it's parameterized by some parameters theta. And it depends on xt, the noisy sample, and the current time. And it's going to try and predict the noise that it thinks was added to xt minus 1 to get xt. So my training process for such a network is choose a random sample, x0, from my training set, choose a random time step between 1 and capital T, and generate some random noise from a standard normal distribution. And then what I'm trying to do is update my noise prediction network, which is the thing here, to minimize the difference between the actual noise and the noise predicted by my network. So, in practical terms, how will this backward diffusion network look? Well, it's a conditional U-net. So I input xt and it outputs what it thinks the noise was that was added in the last diffusion step. But this has to depend on t. So I make my network conditional on t. So if you think about it, the input coming into this network will be very different. So when t is large, I'm going to be getting things that are almost just completely random Gaussian noise. When t is nearly 0, I'm getting things that look like images. So the behavior of the network has to be quite different for different values of t. So that's how a DDPM model works. And we can use it in some ways like a GAN. So we can generate random noise, which you can think is like generating a random latent vector for your GAN. So that would be spatial noise in this case. And then I would repeatedly pass it to my denoising U-net with a decreasing value of t each time. That will allow me to estimate the noise that I need to be able to move to a slightly less noisy version of the image. And I repeatedly do that until I reach time t equals 0, and then I end up with a completely denoised image. And if I changed my initial noise, I would get a completely different image. But the idea is that this is now a good model of the distribution of real images. So in practice, this works better than a GAN. So you may wonder why, and there's a few sort of intuitive reasons why. So one is that in a GAN, I just get one forward pass. I input my latent vector, I move through the layers of my generator, and then I have to output an image immediately. However, this denoising U-net, it gets many opportunities to adjust the final image. In fact, a typical value for capital T might be 1000. So in other words, I get to pass through this U-net 1000 times, making different adjustments to the image. So what tends to happen is early in the diffusion process, I can decide sort of low frequency things, like make the decision that there's going to be two cats and that they're roughly in these positions and that there's a pink background. But then towards the end, I get lots of opportunities to add more detail. So as my noise is approaching the final result, I can gradually add that sort of high frequency detail. The other thing is that the 2D latent space, so my 2D initial noise, is quite helpful because it's structured the same as my image, and it's also much higher dimensional than you would typically use with a GAN. On the other hand, there are a couple of drawbacks. It's very slow, so I might need 1,000 forward passes through my denoising network. And another problem is there's no easy way to optimize my latent representation to fit it to data. So if you imagine like trying to find the noise that would give me a particular image, that would require back propagating through 1,000 versions unrolled of this UNet. And now I'm going to suffer from massive vanishing gradient problems. So that just doesn't work in practice, and it would be extremely expensive to implement. So in terms of results, this DDPM method is capable of incredible photorealistic synthesis of things where GANs also do well. So things like faces, where they have very regular structure and they're kind of aligned in some meaningful way, but also much more diverse images like just natural photographs of the real world. It's able to learn that much more complex distribution very well. So the method I've introduced, DDPM, is quite a basic diffusion model, and there have been many efforts to improve it. So just to give you a couple of examples, so denoising diffusion implicit models can take any model that was trained with a DDPM loss, and it's a way of performing the sampling but with some steps skipped. So for example, you might be able to reduce the number of diffusion steps from 1,000 to 50. And it allows you to trade off the quality of the final result against speed, so the number of steps you take. And then a more recent model is the latent consistency model. And the idea is to basically distill the process of backwards diffusion into a much smaller number of steps. It could even be like 2 to 4 or even just one step. So directly predict the result of the entire backwards diffusion process in one step. And the quality of this approach is approaching that of the full DDPM method.